Class was actually at 8 a.m. And I don't know. So there's this girl who showed up. What people used to do is you could skip class. You could get a late pass, right? If you showed up late to high school, they used to hand you out a late pass. So if you wanted to cut physics, you wouldn't show up to class. You'd go and you'd grab a late pass. You'd show up the next day, give them the late pass, and say, I was so late that I missed your class, right? And one day, so this girl shows up and does that, and he goes, "What's this?" And she hands him the late pass. He's like, "What's this?" And she goes, "That's my late pass." He's like, "You weren't here yesterday." She's like, "No, I was late. I was late, so I missed the class." He says, "You should look up late in the dictionary. Late means to come in, but to come in late." And I started cracking up, and nobody else in the class laughed. So I thought that was pretty funny. Right? It was a recursive definition. Right? You can't define late in terms of being late. Late means to come in, but to be late. Anyway, and then he was also describing interference at one point. You know how sound waves, when they interfere with each other, they can cancel each other out. And no one was really paying attention. So he says, so that's why when you sit at a rock concert, you want to sit right in front of the speaker, so you don't miss anything. Right. So again, I thought that was pretty funny, but no one else got it, right? Because right in front of the speaker, there'll be no interference. Anyway, okay. Obviously, many of you have the same sense of humor as my colleagues in high school, or the same lack of sense of humor as my colleagues in high school. I had a really good joke I was going to tell, but I don't remember what it is now. I learned a new joke recently, but a lot of the jokes I know aren't appropriate for class, but some I know are, but I can't think of any right now that are appropriate for class. Okay. Any questions on the homework? Any questions on the material? Nobody's looked at the homework yet, huh? All right. And I have to move my office hour again today, so I will make, actually, 4:30. I'll be available at 4:30. Okay, yeah. It was going to be 11 to 12, but we have a visitor coming today. Again, and I'm hosting the guy, so nobody else could meet him at 11. I have to meet him at 11. 4:30 to 5:30 to 5:45. Or send an email, although, right, again, my email turnaround time is like 3 days, so I may get back to you by Saturday. Plus, Friday is, Saturday is the Jewish holiday. So, not supposed to be checking email then, so maybe I'll wait till Sunday. Okay. So no questions. Okay, so we left off, we were talking about the exponential distribution. Right, with the brother who can see and the brother who's blind, they both jump. They're both equally likely to go the same distance. Okay, I think that if I just said if I instead explained it to you in terms of light bulbs and said you start with a light bulb, it's on, it's burning, it's been burning for a year. You put in another one and turn it on. They're both exponentially distributed with the same rate, lambda. They're both equally likely to last the same amount of time. Probably doesn't help with the recall as well, right? Light bulbs, boring. The blind brother and the brother who can see jumping, exciting. Will help you remember. All right. Exponential distribution. Exponentially distributed random variable with rate lambda. Exponentially distributed random variable x with rate lambda satisfies probability x. Let's use t. Probability x greater than t equals e to the minus lambda t. I don't know how mathematicians came up with these terms like satisfies. There's always these weird terms that we use. But after you learn them, you always use you know which ones to use. But it just, I don't know. Again, it gives like a human element to this satisfies this. I mean, this is satisfied as a result. I don't know. All right. All right. Anyway, but so we say satisfies. Okay. Right. So, and we also mentioned that it satisfies the memoryless property. Which you can think of as the probability that x is greater than t plus s given x is greater than s is the probability that what? X is greater than t. Yeah. Right, the memoryless property said the probability that we have to wait for more than time t plus s, given that we've already waited at least time s, is the probability that x, we restarted the experiment at time 0 and have to wait an additional time t. Right, if here's s and here's t, the probability that you got to wait beyond this amount of time, given that you've waited beyond this amount of time, is as if you just started at this time, and it's the probability that you had to wait beyond time t, given that you started at this time. That's to sort of be. My dad showed me that trick. If you want to find the camera, you try. If the guy moves the camera, hang on. You try. You point at it, right? You wait till your finger points at it, and there it is. Learned that when I was 5. I thought my dad was a really smart guy. He is a really smart guy, but he's done smarter things than show you how to find cameras. But anyway, try it sometime. Try it without pointing. It'll take you forever. Anyway. Okay. Okay. So probability that if you start at time 0, that you go beyond time s plus t if you're an exponentially distributed random variable. Given that you've gone past time s, is as if you started at time s and just went past t. That's a property of the exponential distribution, not a property of other distributions, right? Certainly not a property of the uniform distribution, right? Okay, so some other properties satisfied by exponential distributions. If x and y are independent random variables that are exponentially distributed with rates lambda and mu, respectively. Okay, they're independent, so the probability that x is greater than y, x is greater than y, x is greater than s, and y is greater than t, okay, because it's independent, it's just the probability that x is greater than s, probability y is greater than t, is just going to be e to the minus lambda s plus mu t. Okay, again, it's e to the minus lambda s times e to the minus mu t. So it's you just add the exponents. You'll find that comes in handy. Okay, hint hint on homework problem number 2. Homework number 2, problem number 1. That will be very useful. Somehow that ties in with minimum. So think about that. All of a sudden that becomes a lot more important, right? Question? Problem 2, sorry. Yeah. Problem 1 we'll get that's also a very easy problem. But we'll see why in a bit. Okay. Suppose Okay, suppose x and y. Let's make Professor Kaufman happy. Represent the lifetimes of 2 light bulbs. This probably not. This is a very Is it which one? What's the probability that
Something like that, like two light bulbs. One burns out, and what's the probability that the other one burns out too, or something.
Yeah. Okay, that probably has more. He's probably more dealing with the memoryless property. So we're doing something else. Let's just get to it. Okay. Suppose x and y represent the lifetimes of 2 light bulbs. Light bulb x and light bulb y. Whose lifetimes are independent. Okay, that's always important. And exponentially distributed with rates lambda and mu, respectively. What is the probability that x is greater than y? I.e., what's the probability that light bulb x lasts longer than light bulb y? Does anybody know the answer? What if lambda equaled mu? What if lambda equals mu? What can you say about the lifetimes of the 2 light bulbs? Huh? Yeah, if lambda and mu were equal, right, the light bulbs have identical distributions. So there's no reason to favor the lifetime of one light bulb over the other. So, okay, so this would equal 1/2 if lambda equals mu. Right, identical light bulbs. So the probability that x burns out after y is 1/2. Because they're identical. So they each have equally likelihood of burning out. What if lambda is super huge? Okay, meaning we're sending lambda to infinity, and mu is super small. So mu goes to 0. What does the probability go to? So that's the limit as this happens of the probability that x is greater than y. We at least get a guess. 0. Yep. Why? Yeah. Yeah. I mean, okay. So the intuition is remember we called these parameters the rates. Okay, and there's a reason why it's the rate. So the higher a rate of something, the faster, the sooner it happens, right? If I told you that the rate of decay of this light bulb is, I guess it's not a good example. So I say the rate is 500 years versus 0 years. I don't know. The rate at which the wires burn out is 500 units of wire per second or something, right? So the bigger the rate, the sooner it burns out. Anyways, if you plot the distributions, okay, so e to the minus e to the minus lambda t, with lambda very big, looks something like this. And, sorry, other way around. It goes like this. Okay, so that's e to the minus lambda t. And e to the minus mu t is going to decay very slowly. There's a slow rate, so it's going to look like that. Okay? Or you can think of it this way. The probability that x is greater than e to the minus lambda t, okay, is equal to the probability, just take logs of both sides. Log of x is greater than minus lambda t. Okay? So if lambda is very, very, very big, right, then x has to be very, very, very small. Or x is more likely to be small. Okay? Anyway, let's get on with it. Okay, so what is the probability that x is greater than y? Right, that was our original question before I got off track. So what if you wanted to go about computing this? If you didn't know the answer off the top of your head, does anybody know the answer off the top of their head?
Yeah, mu lambda plus
Yes. Okay, also very nice, right? These are exponentially distributed. They have these weird distributions, e to the blah, blah, and the probability that x is greater than y when x has rate lambda and y has rate mu is mu over lambda plus mu. Okay, if you wanted to solve that, how would you do it? Well, you'd have to use a density function. So the probability that x is greater than y. Okay, this is sort of the brute force approach. Equals the integral from x equals 0 to infinity, and y has to go from y has to be less than x, right? We're solving probability y is less x is greater than y. So y goes from 0 to x. Okay. Again, we don't care about less than or equal or at the point where they're equal. So the point where they actually match up, that's fine. You could put greater than or equal to if you want, or greater than, doesn't matter. Okay. Of what? Of the density that y equals y times the density of x equals x. dy dx. We're doing a double integral. They're independent, so we can split the densities. Okay, they follow the same sort of independence rule. Or you might be able to see this right away. The probability that x is greater than or equal to y is equal to the integral from y equals 0 to infinity of, sorry, let's do x equals 0 to infinity y. Y equals 0 to infinity of the density that y equals y. Okay, so we're going to integrate when y equals this value, and now we just have to make sure that x is larger. Okay, and that's times the probability that x is greater than, well, we can say little y. dy. So we're integrating over all the possible values of y. We're going to let y take on each of those values, okay? And then when y equals y, all we have to do is make sure that x is greater than y, that little y, okay? People see that? And when this is true, when y equals this value y, you just have to make sure that x is greater than this little y. Yeah, Ari?
Why would you assume that those two events are independent? Why would you assume that the event that y equals y is independent of that x is greater than y?
The little y is just a number, right? And these are capital X and capital Y are independent random variables. So it would be as if I asked, I mean, in this case, I'm asking density that y equals 0.07, probability that x is greater than 0.07. Since those are independent random variables, you can split it apart. There's nothing special about the value 0.07. I could ask, what's the density that y equals 0.07, probability that x is greater than 15? Because x and y are independent random variables. I just happen to only be checking with the same number here. That's how you solve this integral. Okay? So if you remember, the way you compute the density of y equals y is you take the derivative with respect to y, the probability that y is less than y, which is d dy of e to the minus lambda, 1 minus e to the minus lambda y, which is lambda e to the minus lambda y. Sorry, mu, everywhere mu. Right? So this integral, the probability that x is greater than, where'd it go? The probability that y equals density y, that's mu e to the minus mu y. And then the probability that x is greater than little y is e to the minus lambda x, e to the minus lambda y, sorry, dy for little y equals 0 to infinity. Okay? Which is just the integral y equals 0 to infinity of mu e to the minus lambda plus mu y dy. If you do the integral, right, this drops to the, divide out by, when you take the integral of an exponential value, this drops to the bottom. You integrate from 0 to infinity. Well, let me do it. Which equals mu, negative of that. Okay, from 0 to infinity. When it's infinity, this term is 0. When it's 0, this quantity here is 1, so you get mu over lambda plus mu. Okay? Okay. Any questions? Okay, let's review Markov chains. Markov is the guy who came up with the really liked this idea of memoryless property and really took advantage of it. Okay, so what is a Markov chain? A Markov chain, Markov chain, is that the general term? Markov chain. What's it called? Markov chain. There's something that's more general. Just blanket on the term. Markov model? Must be Markov model. Okay, you have states and transitions. And So for those of you who has never seen a state machine, it's a lot like state machines, right? Where every state represents something, and you can move from state to state. Maybe even have a self loop. Maybe go back where you came from. Okay? So here's an example of a Markov chain. And it could represent, for instance, the floor that an elevator stops on. So I guess for the building, elevator and steps are 4, 6, 7, 8, 9, 10. Okay, obviously there are probably a lot more transitions for the real elevator. But what this is saying is from floor 4, the elevator can take you to either floor 10 or to floor 6. Okay, and then from floor 6, you can go from you can either go to floor 7 or back to floor 4 or to floor 8, etc. Okay, and the important point about well, we're not there yet. But everybody get the idea of the states and the transitions? Okay, so this is what we call a state machine, finite state machine. And Markov chains, Markov model, you have transitions are taken stochastically. Gesundheit. I.e. with some probability. Okay, so you may have seen state machines before where there's some input sequence that tells you how you move around. Like people get in the elevator and they say, I want to go up, I want to go down, I want to go to floor 8, I want to go to the closest floor 9, whatever. And then the elevator takes them the right places. All right, here it's just probability transitions. So there are two variations. There's a discrete Markov chain, discrete probability, and our Markov model, and continuous time, discrete time. Okay? The difference is how we label the transitions. So discrete is probably the easier one to start with. So again, I got a bunch of these states and a bunch of transitions. Maybe even a self loop. And number of the states. Every transition has some probability attached to it. 0.2, 0.8, 0.7, 0.1, 0.2, 1, 1. Okay? And what this says is you sort of imagine a clock ticking, okay? And every time the clock ticks, you're in some state, you have to take a transition. Okay, each tick of the discrete clock, take a transition. Okay, so I may start in state 1, which the way I drew the diagram you cannot leave from. So let's modify that. Let's say you go back here with probability 0.4, here with probability 0.2, here with probability 0.4. Okay, start in state 1. I flip a coin or run my random generator or something, whatever can give me the you know, or play cards to get these appropriate probabilities, and I transition to the next state. So from 1 I go to state 2 with probability 0.4, with state 3 to probability 0.2, with state 5 with probability 0.4. And then whatever state I wind up in, I flip my coin again on the next clock tick and move to the next state. Okay? Pretty easy concept. Some of the probabilities, and also the self loop. So if I'm in state 3 and another clock tick with probability 0.7, I'm allowed to stay in state 3. And the way I've drawn this Markov chain, you can't stay in the same state if you're in any other state, right? You have to move somewhere else because none of the other states have self loops, self transitions. Okay? The sum of the probabilities exiting a state sum to what? 1. Yeah, you got to go somewhere, right? So if with probability x I go here and probability y I go there and probability z I go there, it has to sum to 1 because you have to go somewhere. And it can't sum to more than 1 because you can't. And you get it, right? I mean, it doesn't make sense. Okay, the sum of the probabilities entering a state. Sum to what? Huh? No, well, greater than 0. Greater than or equal to 0. Yeah, there's no restriction. And just to see that there's no restriction, okay, I could create a Markov model with as many states as I want. So zillions and zillions of states. And I could have everybody move this way with probability p, okay? And then with probability 1 minus p, everybody goes back to state 0. Right? So the sum of the transitions in are this 1 billion zillion times 1 minus p. So right, that could be as big as you want, for instance. And you could have no transitions going back to the state, in which case the probability of going back there is 0. But then it's not a very interesting state, right? Because you never go back to it, so it becomes pretty useless pretty quick. Because we're going to be looking at what are called steady state distributions. We'll get to that in a bit. Any questions? Okay, continuous time Markov model. Markov chain, Markov model. Really, I'm doing Markov models. So, transitions are labeled. Is there 2 L's or 1 in label? Or 2 L's here or 1 in labeled? 1? You sure? Okay. I need spell checkers, like when I write papers and stuff. It's horrible. All right. Transitions are labeled with rates and time spent and a transition. How do I say this? And the activation time of a transition is independent of other activation times and is exponentially distributed with rate assigned to that transition. Okay, so I can have a Markov model, again with a bunch of states. No self loops. And then there are rates assigned to the transitions. 10, 2, 4, 0.072, pi, square root of 12, 15, 6. That's a pi, not an a. Okay? And all that says is when I'm sitting in this transition, okay, I run two exponential, think of it in terms of time. We're going to be doing a lot of things with exponential distributions in terms of time. So it's worth thinking about it that way. So, okay, Professor Kaufman takes his two light bulbs, puts them in. Okay, this light bulb's rate is 6, this one's rate is 15. At some point, some light bulb blows out, and you follow the transition to the next state. Okay, so you spend a certain amount of time in each state, and when one of the transitions triggers, the first one to trigger, that's the one you take. Okay? So we're waiting here, and then after some amount of time, this one will trigger with likelihood 6 over 6 plus 15 is the likelihood that this one will trigger first with likelihood 6 over 6 plus 15. This one will trigger first with likelihood 15 over 6 plus 15, right? Going back to what we did before. But the reason why what I'm talking about is lambda over lambda plus mu is because it's the probability of which one is less instead of which one is greater. You with me? Okay, so you take that transition with that probability, move to the next state, sit in that state for a certain amount of time. Eventually, this one only has one transition, so after a time that's exponentially distributed with rate 10, you go to this transition, and then again, depending on which one of these fire first, you take that transition first. Okay, and so what's so lovely about the Markov models? Anybody here ever see Kentucky Fried Movie? Jeez. It's a really funny movie. Anybody here ever see Bruce Lee's, what was the last movie he made? Enter the Dragon? Anybody ever seen that? So it's a spoof on that. So I'll tell you one scene that I think is really funny. So in the Bruce Lee movie, right, the head bad guy takes Bruce Lee down to his dungeon. Actually, there's a couple of things that are fun. But one of the things is he goes, he has these guys locked in a prison. He says, these guys don't know where they are and don't care. Okay, so that's what he says in the Bruce Lee movie, right? And then in Kentucky Fried Movie, which is a spoof on it, the guy's got 2 jail cells. He goes, these guys over here, they don't know where they are and they care. And these guys over here know where they are and don't care. These guys over here don't know where they are, but they care. Okay? So then they walk away, and the guys in this one, the guys who don't know where they are but care, goes to the other guy and says, where are we? And the other guy goes, I don't care. That's always funny. And we'll get to why that's relevant in a minute. There's also a scene where in the original movie where the head guy's bodyguard, his name is Chang, and he's tough and ruthless. Okay, and in the movie they go, this is his in Kentucky Fried Movie they go, this is his bodyguard Chang, he's tough and ruthless, and this is his driver Wang, he's rough and toothless. You see the movie. The movie's fun. But you should see this. See the Bruce Lee movie first, because then it's a lot funnier. Okay. Anyways. So what's the relevance of that? That whole story is the memoryless property of Markov model. Okay, remember, in both versions, when we make a decision to transition from here, right, to go to the next state, it didn't really matter how we got to that state, right? So if this state asks, how were you reached? So this is A, this is B. So he says, hey, A, how'd they get to you? Right? And then A will respond, I don't care. Because it's memoryless. Hence the Kentucky Fried Movie story. Right? So even though it kind of seems obvious from the picture that that's the case, it's only the case with the exponent. It's because these times that we sit in these states are exponentially distributed that we don't have to remember where we came from. Okay, so let me so okay, let me show you why we like the exponential distribution so much better than uniform. Okay, so imagine this. Imagine you're waiting for the red bus and the blue bus. Okay, and they take turns coming. It's the red bus, then the blue bus, then the red bus, then the blue bus. So when we're in this state, the red bus is next. Or in this state, the blue bus is next, right? And we're going to transition back and forth between these two states. Okay? So now, suppose the buses arrive every hour, or the buses arrive, one bus arrives within each hour. The time at which it arrives is uniformly distributed. Within each hour. And the arrival time is uniformly distributed between 0th and 60th minute. Okay? So fine, it's 5 o'clock, the red bus is next, we're sitting in this state. And at some point the red bus comes. It's uniformly distributed time, right? Okay, the red bus came. Now let's go to this state and wait for the blue bus. Okay? How long do you have to sit in this state for? I mean, we came at 5 o'clock exactly. Okay, so we know that the amount of time we sit in this state is uniformly distributed between 0 and 1. Okay? Now the bus came and went. Now we go to this state. It's before 6 o'clock. How long do we have to wait? Well, we have to wait until 6 o'clock. All right. However, it depended on the time that this red bus came. Right? The amount of time we have to sit in this state depends not only on how long it takes the blue bus to come, but also how long it took for the red bus to come. Right? People see that? That's why the uniform distribution sucks compared to the exponential distribution. So for the exponential distribution, okay, here's red, here's blue. Okay, they both are, let's say now the arrival time of next red or blue bus. We can even make it different distributions, different rates. Is exponentially distributed. The arrival time of the next red bus is exponentially distributed, or the time to wait, let's say. Time to wait until next bus. After previous blue red bus arrives. People understand this parentheses notation? Like I'm saying red here is blue here, or you can go by what's in the parentheses, blue, red. Okay? So it's exponentially distributed with rate, lambda, or mu. Okay? So this system can be modeled as a Markov model, where the transitions are red, we said, we're waiting. Time to wait for the next red bus is lambda. Do this right? Yeah, because after the red bus comes, I immediately take this transition, and I'm waiting for the blue bus. And the time I wait for the blue bus is exponentially distributed with rate mu. Okay? And now this is memoryless. So the red bus eventually comes. Okay? And I take this transition, and now I'm in this state. And how long do I have to wait for the blue bus? Well, it's some time that's exponentially distributed with rate mu. Doesn't matter if the previous red bus came instantaneously or it took 12 years. Okay? It doesn't affect how long I have to wait for the blue bus. So this is captured by a Markov model, and this is not. So this cannot be captured by Markov model, despite the fact that I drew it. Okay. Yeah, Ezra.
Uniform one is not. Eminalism.
Yeah.
Even then you wait for it to come back.
No, but I'm just watching the buses go by. Okay, and I'm asking how long do I have to wait until the next bus? From the time of the last bus. So suppose the times are uniformly distributed within hour intervals. Okay, so a red bus comes. It comes at 5:28. How long do you have to wait until the next blue bus? Well, it's going to be 32 minutes plus a value that's uniformly distributed between 0 and 1.
Instead of the bus arrives every hour and the arrival time is uniformly distributed, but the time you have to wait is uniformly distributed, and that would also be manually.
Yeah, so let's so fair enough. So not a good explanation. That's true. So I did a poor job explaining the difference. So let's see. Okay, let me everything I've told you about Markov models is correct. The only thing that's still unclear is why the exponential distribution is so much better than the uniform distribution. So let me think on that one. Let me think up a good example. But that's a very good point. Yeah, Ron.
The reason, based on your initial problem, what you said, are you saying that exponential is better because for uniform you have to wait till the hour turns over before you can start counting towards the new one? Because it's 1 over...
Scratch everything I said, starting from this board and this board. I mean, it's just not a clear distinction. So forget about this and this. Everything else still holds. I stand behind everything else I said. Unlike politicians, professors can take back what they say, right? Politician puts it out there, you're stuck with it. Professor? Some professors think they are, but you're not really. Yeah. Is it Ari or?
In the Markov model, when do they start? When you get to the node, or when do they all start at the same time, all the distributions? Do they all start at equal 0, or?
When you arrive at the state, yeah. well, let's pick one. When you arrive at this state, I didn't label any of them, but yeah, all the clocks start running on all the transitions, and whichever one fires first, that's the one you take.
All the other transitions are running at all?
Well, if it's exponentially distributed, it doesn't matter.
So that means
It doesn't matter if it's exponentially distributed because, I mean, if you're not in this state and this transition fires, what do you care, right? If it fires and you start it up again immediately, and then you arrive to that state, how long this transition has been running for before you arrive doesn't matter. Yeah, but that's not really. Let's keep going, and maybe something will strike me as to why it's so different. Okay. So let's actually look at a Markov chain. For instance, people standing in line. Okay, so you can have 0 people standing in line, 1 person standing in line, 2 people standing in line. Let's say the maximum size of the line is n. Okay. Max size of n. A new person arrives at time tick t. New person arrives with probability p, and a customer can be served. With probability 1 minus p, if a customer exists. So at time 0, with probability p, a customer will arrive at the next time tick, and with probability 1 minus p, the customer is not served. Okay, so and since there are no customers in the queue, it transitions this way. Okay, so we have p every time. Okay, so those are all p. And then with probability 1 minus p, if there's a customer in the system, they get served. And here, also with 1 minus p, you go to, let's put n minus 1. Okay, so think of it this way: the person managing the queue, either they can serve the customer at each time tick, or they can scream out next and bring someone else onto the queue. Okay, one or the other. They can't do both. And if they scream out next and there's already n people on the queue, you can't go anywhere. So you just stay at that length. There's only room for n people. So even if the person screams out next, nobody else can come in. Okay, so it's kind of a weird queuing system. Okay, so you start wherever you want. Let's say we show up when there are 2 people. With probability p, you'll go to 3. With probability 1 minus p, you go to 1, etc. Right? Everybody understand the model? Okay. So let S of t be a random variable that equals the state the system is in at time t. Okay? So suppose I tell you S of 0 is 0. We'll start off with the queue being empty. What's the probability that S of 1 is 0? So what's the probability we're still in state 0 at time 1? 1 minus p, yeah. It's the probability, so we're in state 0 at time 0. We have to take this transition to stay in state 0 at the next time step, right? So probability 1 minus p. What about the probability that S of 1 is 1? P, yeah. It's the probability we take the other transition. What about the probability that S of 2, S of 1 equals 2? 0. You can't get there. I mean, obviously, these two sum to 1, so the probability of everything else is going to be 0. You just can't get to any other state. Can't get than 1. Okay? What's the probability that S of 2 equals 0? Huh? We'd have to go to the state it was in before, right? Kind of, right? 1 minus p. How'd you get that?
1 minus p squared plus p minus
Yeah. So this happens if transitions go 0 to 0 to 0. You stay in 0 the whole time, or 0 to 1 to 0, right? The only way I can wind up in state 0 at time 2 is if I stay here, if I go, or if I go here and then back to here, right? So each step is independently chosen, okay? So the probability I stay here both times is the probability I take this transition and that I take it again. So it's 1 minus p times 1 minus p. And the probability that I do that path is p times 1 minus p. Okay? So it's going to be 1 minus p squared plus p times 1 minus p, which is just 1 minus p, if you do some algebra. Okay? What's the probability that S of 2 equals 1? One minus p times p. Yeah. There's only one way to do it. Only one path. You have to stay in 0 and then go to 1. Right? And the only other place you can reach in 2 hops, 2 time ticks, is 2, which would be p squared. Right? Both times you go that way. And you keep doing this. It gets complicated rather quickly. Right? What's the probability that S of 3 equals 1, 2, 3? What's the probability S of 4 equals 1, 2, 3? What's the probability that S of a million equals 1, 2, 3, 4, 5? Okay? But if your Markov chain or Markov model is what's called ergodic, and we will only consider ergodic ones. I'm not going to bother explaining what ergodic means. It basically means that you can say, then there is a steady state probability. Pi sub I. Pi sub I is by definition the limit as t goes to infinity of the probability that S of t equals I. Okay? I let this thing run forever. And then I ask, well, and then I just stop and say, what state am I currently in? And if the Markov chain is ergodic, then that probability approaches this steady state probability. Okay? So a real simple example. Suppose I start this off in state 0. What's my steady state probability for state 0? Suppose I run this thing for 100,000 time clicks. And then I stop it. And I say, where is my, what state am I currently in? What's the probability that I'm in state 0? Yeah, Ari.
Maybe 1/2 by symmetry?
1/2. Yeah, exactly. The fact that we started in 0 is history from a long time ago. So you're equally likely to be in each state. So here, the probability, we could just say that pi sub 0 is 1/2 and pi 1 is 1/2. I mean, basically, the point is when you run it for a long time, where you actually started doesn't matter anymore. Okay. And right. So let's go back. Let's go back to our previous Markov chain up here. So for our Markov chain on the left over there. What is the probability? Let me say, what is pi sub I? Okay. Well, I'm obviously not going to cover coding today. So let's make the due date for the homework next Wednesday. Which is what? September, is it October already? September 29th. All right. Okay, so how are we going to solve this? I always like to show people when they're pretty easy way to prove things. I think it's important to, you can just put up the formula, but I like people to understand the formula. All right, so let's just go through the process of seeing why this is the case. Okay, so the observation we're going to make is what's the probability that that at time t plus 1, you're in state I. Okay, for some state in the middle of that system, it's going to be the probability that at time t you're in state I minus 1 times p, right? I could have been, what's probably I'm in state 2 at time t plus 1? Well, if I was in state 1 at time t minus 1, or sorry, at time t, and I take this transition with probability p, I wind up in state 2. Or I could be in state I plus 1, and with probability 1 minus p, I transition back. Right? This is for I. This is for 0 less than I less than n. And for I equals 0 is what? It's 1 minus p times the probability that s of t equals 0 plus the probability plus p plus 1 minus p times the probability that s of t equals 1, right? And the probability that s of t plus 1 equals n equals, where are we? P times the probability that s of t equals n plus p times the probability that s of t equals n minus 1. right? So now take limits as t goes to infinity. Okay, so what happens? P of s of t plus 1 equals I. The limit of that as t goes to infinity, well, that becomes pi I. That's definition of pi I. Right? Pi I is the steady state probability that we're in state I at time infinity. And if the steady state probability exists, it doesn't matter if you're taking t plus 1 to infinity or t to infinity. Okay, so which also equals the limit as t goes to infinity of p to the s of t equals I. Actually, well, we defined it this way. But clearly these two are equal, right? As t goes to infinity, doesn't matter if you're looking at s of t plus 1 or s of t. Right? Again, thinking back to this example, I let the thing run for this huge amount of time. Then I stop it, and I ask it, okay, at time t, what's the probability I'm in this state? Well, it's this pi sub I. Oh, what about at time t plus 1? Well, it's the same thing. Okay, if this steady state probability exists, it means that after you run it for a long time, that's the probability you're in that state. So if you run it for one more time tick, it doesn't matter. Okay, so we can rewrite all those equations in after taking the limits. So you got that pi sub I equals p times pi sub I minus 1 plus 1 minus p times pi sub I plus 1 for I for 0 less than I less than n. And you've got that it equals 1 minus p times pi 0 plus pi 1 for I equals 0, and p times pi n plus pi n minus 1 for I equals n. Okay, so let's look at this for a second. I have that pi naught equals, where'd it go? 1 minus p times pi naught plus pi 1. Right? So I can solve for pi 1 in terms of pi naught, or vice versa, but let's do it that way. Pi 1 is going to be pi naught, am I doing this right? Pi naught minus 1 minus p times pi naught over 1 minus p. Just some algebra. Okay, which is just going to be p over 1 minus p times pi naught. Right? And let's now try to solve. So that gives me pi 1. So what about pi 2? Let's see, how do I want to solve for pi 2? Well, I have this equation. Use pi 1 equals, where is it? P times pi naught plus 1 minus p times pi 2. Okay, if you do a lot of algebra, which takes a lot of time, so I'm just going to skip it, you're going to get that pi 2 equals p over 1 minus p squared times pi naught. Okay, if you keep doing these all out, you're eventually going to wind up with pi sub n is going to be p over 1 minus p the n of pi naught. right? So we can solve everything in terms of pi naught, right? How do we solve for pi naught? The value of pi naught. It's something we haven't used yet. Suppose I have a two-state system. So let me call the states A and B. I got some transitions and lambda and well, p and 1 minus p. Suppose I told you the steady state probability of A is 0.37. What's the steady state probability of B? I stop the I let it run. Yeah, run. 0.63, right? I run the system for a long time. I stop and I take a look at the system. And I ask, what's the probability that I'm in this state? That's how the steady state probability was defined, right? So I got to be in some state, so they got to sum to 1, right? So that's what we haven't used. All these pi sub i's sum to 1. I equals 1 to n, I equals 0 to n, pi sub I equals 1, right? So you can write that in terms of pi naught. P over 1 minus p to the I times pi naught equals 1, right? Or 1 over pi naught equals the sum from I equals 0 to n of p over 1 minus p to the I, which equals what? Does this look familiar? Sum I equals 0 to n of x to the I, right? It's 1 minus x to the n plus 1. So in this case, it's 1 minus p over 1 minus p to the n plus 1 divided by 1 minus p. Sorry, 1 minus p over 1 minus p. Right? Okay, just one last comment. Let n go to infinity, so there's no upper bound on the size of the queue. Okay, you can work it through, but our steady state results still hold. So then pi sub I is just going to be the limit as n goes to infinity of that stuff up there. So the term in the numerator is going to drop out. So you wind up with, sorry, this is pi naught. Pi naught equals 1 over 1 minus p over 1 minus p. So you can multiply the numerator and the denominator by 1 minus p. So you're going to get 1 minus p over 1 minus p minus p. 1 minus p minus the p, which is just 1. So it equals 1 minus p. There's nothing underneath here. And so pi sub I equals 1 minus p times p over 1 minus p to the I. Right? Or, yeah. So those are the steady state distributions. Yeah. P is
Greater than 0.5.
P greater than 0.5.
We can't apply the limit 10 tends to infinity because p by 1 minus p is greater than
Well, that limit doesn't because it's bounded by n. Right? As n goes to infinity, the limit goes to infinity. That's what you're saying. Well, think about it. With a queuing system with no upper bound, if p is greater than 0.5, over time you're just going to keep drifting higher and higher and higher. Right? So the steady state in that case, it goes off to infinity. Whereas if it's less than a half. You know, you'll drift down every once in a while. You'll bump here, and then you'll go back up, and you'll drift back down. Boom. Right. So there is still a steady state. So a good observation. But when it's a finite, when the Markov chain is finite length, then this term is not infinite, right? So you're okay. All right, let me just put a. So that was for finite Markov chains. So let's quickly look at an infinite. That was for discrete Markov chains. There's also the continuous version, right? Where you have rates going back and forth between these two systems. Okay. So now we're just talking about the amount of time you spend here. So the cashier is working with taking care of a customer. Takes time. That's exponentially distributed with rate mu to finish processing a customer. New customers are arriving at rate lambda. Okay. So it takes the cashier time exponentially distributed with rate mu to help a customer and time and customers inter-arrival times are exponentially distributed with rate lambda. Okay? See what I'm saying? Every time a customer arrives, the inter-arrival time is the time until the next customer arrives. That's exponentially distributed with rate lambda. Okay? Now because it's exponentially distributed, we can really take advantage of the memoryless property. So here's where it comes in where the continuous case wouldn't be. Imagine you got buses coming and going in our depot. Okay, how many buses are currently in our station? Well, if the bus spends an amount of time that's uniformly distributed, or if the next bus is going to arrive in a time that's uniformly distributed, suppose a bus has just arrived. So we want to move from state to state to keep track of the number of buses. So we have 2 buses and 1 just arrives. We go to state 3. Well, how long until you move back to state 2? Well, if it's uniformly distributed, we have to remember how long all the buses have currently been sitting in the depot, because that affects how much longer until we have to wait for them to leave. Right? Sorry, did I say uniformly distributed? If it's uniformly distributed, you have to remember. If it's exponentially distributed, you don't have to remember. Okay? Probably because we're over time, you're not going to remember any of this anyway. So we'll just pick it up next time. Start from there.